Okay, good morning everyone. So let's start today's class. Recall that in last class we introduced the basic concept, what is a neuron, and then we mentioned a special type of neuron that is called perceptron. Perceptron is a model of neuron that specifically uses the binary step activation function, this function. So if x is negative, then it only outputs 0. If x is non-negative, then this activation function outputs 1. So that means for this neuron, actually now it's called perceptron. For this perceptron, all the output can only be 0 or 1. And we want to use such a perceptron to learn the logic AND, whose truth table are shown like this. So now we have 4 data points. Right? So each of the data points, actually, we also have their labels. Then we need to know how to learn such a perceptron. Learning a perceptron is equivalent to learn the values of all the parameters here. And we know here we have 3 parameters, 2 weights, W1, W2. One bias term, that is theta. We want to know, okay, what should be the values so that this perceptron can perfectly match with this data. So that means whenever you give one data point to this perceptron, the output should be the same with the actual output. That is, now if you pass 0, 0 to the perceptron, then after all the computation, the output should be 0. And for each of the data point, it should correctly predict that. So we have done one step, initialization, and actually you must be very confused. Why? Why should we just random generate some of the values to these parameters? And if we random generate them, can we update them later so that it can correctly learn the data set? Yes, let's see what are the learning rules for perceptron. So for this perceptron, we know x1 and x2, they are inputs. Theta is a bias term, the bias term associated with this perceptron node. And then we have 2 weights, W1 and W2, right? So the number of weights, of course, should be the same with number of inputs. And we have big O, we use this big O to denote the computed output. So that is the output computed by this perceptron. And we use big T represent the target. Basically, target is just the label. In training data, it's the label. So target, big T, is just this last column, target. And each step, we want to update some of the parameters. Update means that now we should add some change to the parameters. We use this delta to represent the change. So here this delta W1 is the change of W1, delta W2, change of W2, and delta theta is the change of theta. We also need one terminology, it's called learning rate. Learning rate is used to adjust the change for each step. So after we know all these denotions, let's see how should we update all these parameters. So we can just try to separate them into 2 cases, but actually later on you will see the 2 cases are basically the same case. First case, if the output is correct. So that is, now you give an input to the perceptron. After you compute the output, you find that output big O is the same with the target big T. So that means now actually this perceptron can correctly predict for this data, right? In this case, no need to update because it can already correctly predict them. So the weights W1 and W2 are not updated. Actually, the theta is also not updated. So just let everything remain the same because now the prediction is correct. Second case, if you pass an input to the perceptron and you find that the output is incorrect. So somehow after the computation, you find that, oh, T is different to O. That means now this perceptron made some wrong prediction. Wrong prediction, of course, we need to try to modify that. We try to improve that so that later on it can be closer to the correct prediction. Then we update all the parameters according to these rules. So we first compute what should be the change of the parameters. For the weight parameters, delta Wi, we let it be the eta. Eta, recall eta is the learning rate. Eta times the difference between t and o. Note that we treat t minus o, this difference, as arrow. So that means learning rate eta times arrow times the corresponding input xi. For the bias term, it's updated a little bit differently. So delta theta just be the learning rate times the arrow t minus o. You don't need to multiply input, because note that theta, the bias term, is associated to the perception itself. There is no corresponding input for theta, right? So basically just eta times t minus o. And then we know what should be the change to the parameters. So the later thing is just you add the change to the corresponding parameters. Like Wi just be Wi plus delta Wi, theta be theta plus delta theta. And in this one step, you can update all the parameters. So we try to make it clear, so we separate into two different cases, but actually the two different cases are the same case. So that is, you don't need to be concerned whether t is the same as o or not, because anyway, the first case, if t is the same as o, then this t minus o is 0. The actually delta Wi and delta theta is 0 if t is o, right? So actually you just combine these two cases into the same case. You only need to execute the updating rules for each step. So now we know how to update the parameters in one step, but what do we explicitly mean one step? So from these rules, you may roughly get the sense that one step is that you need to pass one training data point to the perception to compute the output. Then you update all these parameters according to the difference between target and the output. So this is called one step. Or equivalently to say that one step is that you pass one data point to the perception, update parameters. Then if we observe our training data, we find that in total we have 4 data points, right? So that means if we want to learn the perception throughout the whole cycle of all the training data points, then we will need 4 steps. After these 4 steps, should we continue, after we pass all these 4 data points to the perception, update them accordingly, should we continue? Yes, possibly we should continue, because possibly in last cycle, the perception made some mistakes. And we want to further examine that whether these mistakes are already corrected or not. That means after one cycle, we go back to the first data point and repass it to the perception and update everything again. And the whole cycle, we call it the iteration, or we call it round, right? The first round means that we need to pass the 4 data points one by one to the perception. So in each round, we will have 4 steps. This is an iterative learning rules. Each step, we do this updating. And each cycle or each round, we execute several steps. And actually, that's why we must need some initializations. If we don't have the initial values for all these W1, W2, and theta, then basically we don't know how to update them, right? We have to update all these parameters based on some initial values, because what we compute is a change to these parameters. So that's why we have to do some random initialization. Only after we have random initialization, we can start to do the updating. So until now, any question regarding the learning rules of perception? Great. So note that the learning rules are for perception, not for some general neuron. So that means if you change the activation function to some other activation functions, possibly these updating rules will change also. So this is we call it specifically for this perception. Then let's try to apply these learning rules to this data set. we will have a big table to record all the updatings. Initially, W1 is 0.1, W2 0.5, theta is negative 0.8. This is our random initialization. And learning rate eta, we just set it to be 0.2. Binary step activation function is like this. And this is our neuron, our perception structure. And then we execute the first step. First step, we pass the first data point. This is round 1, step 1. We pass the first data point x1, x2 equal to 0, 0 to this current perception. And we need to compute the output. Right? Compute output is that we just follow all the formulas to do that. Like in the first step, maybe I just write in the whiteboard to show you the first steps so that you can know. In this case, the output, big O, is the activation function f takes the weighted sum. Weighted sum is, we found that, okay, x1 is 0. And actually, it doesn't matter what is W1, but anyway, we can put it here, 0.1. And x2 is 0, and W2, 0.5, and then theta, negative 0.8. This is not 0, this is big O, by the way. The big O is f negative 0.8, and this negative 0.8 will be passed to the binary step activation function. Let's here, so it should be 0. Yeah, it's somehow confusing. This is big O, this is 0. And then we find that, okay, for this training data, actually big T, the target, that's the actual label, is also 0. Right? So, yeah, for now, this perception can already correctly predict for the first data point. And then everything remains the same. So no change to W1, W2 theta. We just let everything remain the same. Now we go to the round 1, step 2. We pass the second data point 0, 1 to the perception. And then we compute what should be the output. Just follow the same formula here. You first get the weighted sum, and then pass the weighted sum to the binary step function. Find that this big O is 0, which is the same with target. So, it can correctly predict for the second data point. Everything remains the same, no need to update them. So far, our perception has done a great work for the first 2 data points, right? They can correctly predict. And the third one, again, is a correct prediction. So if we pass 1, 0 to perception, we get, okay, the output 0, the same with big T, everything remains the same. So we only have 1 data point left. So that means if the last data point can also be correctly predicted, then this perception is already a perfect match to our training data. But unluckily, when we pass the last data point to our perception, it made a mistake. So we pass this 1, 1 to this perception, and we can try to compute this big O now. This big O is F. Okay, x1 is 1, W1 here is 0.1, x2 is 1, W2 is 0.5, and then theta negative 0.8. And then we find that it should be F negative 0.2, which is 0. So that means after computing in the perception, the output O is 0, which is different with the target 1. Now, our perception made a mistake. It cannot correctly predict for the last training data. That's why we have to update the parameters. And we just update according to the updating rules, if you still remember that. So in this case, we find that, okay, this big O is 0. So we find the arrow. What is the arrow? Arrow T minus O now is 1, right? And now we update them like we get this delta W1, which is learning rate eta 0.2 times this arrow, then times x1, which is 0.2. So that's why we computed delta W1, 0.2 here. We can do the same thing for delta W2 and delta theta. We find that now we should adjust the parameters by adding them with these changes. And after updating them, W1 becomes 0.3, W2 becomes 0.7, and theta becomes negative 0.6. So we make this updating because we believe by adjusting it in this direction, we can make our perception closer to the true labels. So until now, we finished round 1. Round 1, we pass all these 4 training data points to our perception one by one and execute the learning rules. We haven't finished it yet. We haven't reached the convergence yet. So what do we mean in convergence? Convergence to this training data means that all these training data points can be correctly predicted by the perception. But obviously, the last training data point so far cannot be correctly predicted. So we continue, we go to round 2. Round 2, step 1, we restart everything, but of course with the new parameters we have learned. So we pass this first data point again, 0, 0 to our perception. Note that for our perception now, the parameters already become 0.3, 0.7, negative 0.6 because we updated them already, right? And we found that, okay, now T and O are both 0. So far, so good. It's okay. Let's move on to the next step. We pass the second data point, 0, 1, to this perception, and we find that unluckily it made a mistake. So now, this output will be computed as 1, but the target actually is 0. So made another mistake, and the error now is negative 1. So then we try to update the parameters. So after that, we computed delta W1 is 0, delta W2 is negative 0.2, and delta theta is negative 0.2. So we update these parameters, like now W1 still 0.3, but W2 updated to 0.5, and theta updated to negative 0.8. Continue. The third data point, okay, it's a correct prediction, very good. Then the last data point, let's check. After updating, can the perception correctly predict it? Yes. Now, at least the last data point, 1, 1, can be correctly predicted by the perception. We haven't finished it yet because in the second round, the perception again made a mistake. We need to further check whether now it can correctly predict for all the data points. We go into round 3. Round 3, step 1, correct, very good. And step 2, correct. Note that in the last round, the second data point is wrongly predicted, but now after adjusting it, it's correctly predicted. And step 3, correct. Step 4, correct. Only at this point we can stop. That means basically the convergence of a perception means that at some round you found that all the data points can be correctly predicted by this perception. Then this perception converge, and also this perception can learn the training data. So this training data, like these 4 data points, already all correctly classified or correctly predicted by this perception. And at this moment, we can stop. Only after this third round, we can stop because, as you can see, all these 4 data points are correctly predicted. So it's fine that we just stop now. Any questions so far regarding how to manually update the parameters for perception? Great. Perception learning is such a process that all the steps are very clear. Basically, you just follow the learning rules, but the calculations are tedious. You have to do this step by step manually. Of course, we don't recommend you to always do that manually, unless in exams. Possibly in exams, I think only in exams we will ask you to do such like manual updating, but in real world, of course, everyone will do this by implementing it using some codes. So first, let's see how to implement the perceptron from scratch. By the way, starting from the lab 5, that's the perceptron, the artificial neuron, we allow you to use the scikit-learn and allow you to use the keras to do your labs. So that's why we can directly show you how to implement from scratch, because actually you don't need to implement it from scratch. Perceptron, if we want to implement from scratch, here we just import math, this math module, then we define our class perceptron. In this perceptron, we first do the constructor initialization. Perceptron initialization, we need to initialize the weight parameters, bias parameter. So the weight self.w, we let it be a list. But of course, you can also make it the numpy array. Actually, it's better to make it a numpy array. But for this example, it doesn't matter so much. So it's 0.1, 0.5. So this W1 and this is W2. We first initialize them to these two random values. And self.theta, the bias term, we initialize it to be negative 0.2. In the initializer, we also define our self.learning rate, which is 0.2. Okay, we finish the initialization, the setting of our initial perceptron. Parameters should be initialized. We also record the learning rate here. And then we define another method inside this perceptron. It's called response. This response actually is just to calculate the output for any input x. So here x is an input for the perceptron. And then first we calculate the weighted sum, right? The perceptron consists of the weighted sum and activation function. Weighted sum, y is x0 times self.w0 plus x1 times self.w1, then plus self.theta, the weighted sum. After that, we need to pass the weighted sum to our activation function. It's a perceptron, so of course we use binary step activation function. Binary step activation function is that its weighted sum larger than or equal to 0, return 1, otherwise return 0. So if y larger than or equal to 0, directly return 1, else we return 0. And we have done for the response. That is, given any input x, we just use this method to calculate its output. Haven't finished it yet because we also need to write the function for updating parameters. We separate them into update weights and update bias because we know that weights and bias will be updated in somehow a slightly different rules. First, let's see how to update weights. We give x and iter arrow as some input for this function. Here, iter arrow refers to the arrow t minus big O. So that means each step the arrow. And then the weight update will be according to this formula. Wi should be Wi plus eta times t minus O times xi. So basically, just self.w0 will be added with this self.learning rate times iter arrow times x0, and the same for self.w1. Then for updating weight, updating bias, we only need to give the iter arrow, right? Because for the bias, no corresponding input. So bias update follows this formula. Theta is theta plus eta times t minus O. Then self.theta will be added with this self.learning rate times iter arrow. After that, we finish defining the updating rules. But until now, we only have some helper functions. Like this response is a helper function to calculate output. These two functions are helper functions to update parameters. We haven't tried to formalize what is a training process. So we have to write another function train so that we can just coding all the training process in such a function. So this train, we pass data, which is our training data. We pass this data to this train, and then we started to train. We have learned this is a Boolean variable. Initially, it's true. This learned is an indicator. This indicator used to indicate whether we are still in the learning or not. If learn is true, that means we should still perform training. And round refers to like which round are we currently now. Initialized round, of course, is 0. And then we start to do the training. We know the training is some iterative process. So we must do it like by some loops, right? There is some rounds. And for these loops, we just use the while loop to implement the iterative process. So while learned, we just let it to be true. So while we are still in the training process, we execute the learning. Total error is 0. So we initialize this total error to be 0 at the beginning of each round. And then for x in data, for each data point in our training data, we let R be self.response x. Response is here. So we pass one training data point x to response, compute its outputs. The outputs can only be 1 or 0. So this R is self.response x. And we compare the target with the output. Target will be stored in x2. So basically, x has 3 dimensions. x0 is the first input, x1 is the second input, x2 is a label, the target. So if x2 is not the same with R, if they're different, an error occurred, we need to update. So we let the round arrow be x2 minus R. So this is the arrow, right? Basically, that's t minus o. And then we update all the parameters. First, update the weights. We call this self.update weights x round arrow, and then update bias, self.update bias round arrow. After that, we compute the total error. So for each iteration, we initialize total error to be 0. Now the total error will be added with this absolute value of round arrow. Update the total error. And after we finish this for loop, these 4 loops are the steps, right? So for x in data means that we need to pass all the training data points in data to the perceptron to update. So after we finish in these 4 loops, basically we finish one round, finish one cycle of the whole training data. We let round be added with 1. We are not finished yet. At the outside, we have a while loop to check whether learn is true or false. Initially, it's true, of course. Then when should we terminate? Like when should we break out this while loop? We need to check the total error. Total error is that for each step, we add the absolute value of round error to it to examine whether in this iteration we have error or not. So if we find that math dot is closed, total error 0, that means if like total error is already 0, or another termination condition is that if we find that somehow the round already larger than or equal to 100. This 100 is we set a maximum iterations. We don't want to like go too many iterations. It costs too much computation power. So we just set these 2 termination conditions. So any of these 2 conditions is satisfied, we will directly print out the total number of rounds and the final weights, which is self.w, final bias, which is self.data, and then we modify this indicator learned to be false. So after we reach any one of these termination conditions, learned will become false. That means now we will break out of this while loop, stop the training process. So this is how we code the train process. Basically, we need some nested loops, of course, because there are iterations, and inside iterations, we have like all these steps. This is how we implement it using the just from scratch. And let's see how to call this class we have just defined. the main function will be like this. First, we create an object perceptron from the class perceptron, and our train data is like this, right? We have 4 data points. Each data point, these first 2 values represent the inputs, and the last value represents the target, the label. This is just the truth table of the logic AND. And then we call this perceptron dot train set. Give this train set to the train function, here, so that it will start to execute the train. And after that, after we run this line of code, it will start to do the training, and it will perform 3 iterations. Then it terminates. Everything will be exactly the same with our manual calculation. So at the end, when it prints the final weights and final bias, you will find that the final weights and the final bias are exactly the same with our manual calculations here, because we already fixed the initialization of the weights and bias. So all the calculation will just be the same. So any questions so far regarding this implementation from scratch? Great. So for this implementation from scratch, it's good to use it as a practice, but it has severe limitations. Of course, the limitation is not that you have to do it by yourself. The limitation is that after you implement this perceptron, it can only be used to learn such a structure. You already fixed that, okay, now I only have 2 inputs, right? What if like the inputs increase? What if you are dealing with some like higher dimensional input? Then it's hard to modify this, right? So basically it's quite fixed, quite specific to this one application. Of course, it's not practical that whenever you have a new task, you implement another perceptron this class. Not practical. The more practical way is that we directly use scikit-learn to do this. Because in scikit-learn, everything like is already implemented, ready for you to use, and you don't need to fix the number of inputs or the dimension of inputs you have. So yeah, everything will get much easier now. So import numpy, and then from scikit-learn.linear model import perceptron. Yes, from this importing, you will already find that actually perceptron is a linear model. Yes, it's a linear model. If you check what we have done in the perceptron, first we do a linear transformation, the weighted sum. After that, we pass this linear transformation to the binary step. Everything just is linear. So perceptron, yes, is indeed a linear model. So after that, we can already use this perceptron from scikit-learn. So we form our inputs, these 4 data points, and their outputs. These are the labels, the expected outputs. And then we just create a perceptron model like this. Let model be perceptron. We already imported it. Perceptron, eta 0 to be 0.2. Eta 0 is the argument for learning rate. So just let eta 0 be 0.2. And after that, run this one, model dot inputs, outputs. Pass the training data and the training labels to fit function. We already mentioned for many times, fit in scikit-learn just means train. They use this fit. All right, after we run this model.fit inputs, outputs, it started to train. So that means now basically it just executes the previous iterative algorithm, do these nested loops to update all these parameters. After that, we can use the trained model to predict the outputs. So let the predicted outputs be model.predict. Then again, pass these 4 data points to this predict function. And we can also try to print this predict output to see what should be the predictions. After that, you will find that the predictions will be 0, 0, here is 1 here, 1, 0. So that means all of these 4 data points will be correctly predicted after we finish training using scikit-learn's perceptron. At the end, you can also print the final weights and final bias to see what are the parameters. So the final weights in perception, in scikit-learn's perception, is called this co-if. Use this to represent, okay, we want to get these weights. And then the bias is called intercept. So use this to indicate that now you want to retrieve the bias. After you run this code cell, after you get the weights and bias, you will find that they are different ways your manual calculation just now. Anyone knows why? Why this final weights and final bias just becomes like different? Any guess for this? So when the final results get different, but still it's a correct perception, right? It can still correctly predict for all of these 4 data points, but the weights and bias are different. First of all, that tells us one thing. Actually, if you want to use a perception to learn a training data, the correct perception is not unique. Possibly you can find many different perceptions that all correctly predict for training data. Actually, for this example, there are infinite number of correct perceptions for this training data. And then let's figure out why they are different, why the weights and bias is just different. When something different, the possible reason, the most probable reason is that there are some randomness in the algorithm. Due to some randomness, the final results will change. And what are the randomness here? Like, what is the difference between this implementation with our previous implementation from scratch? You find that because of the initialization. In our implementation from scratch, we initialize all these parameters. We just fix, okay, now the initialization should be these 3 values, and starting from these 3 initialization values, we start to update them. But in this scikit-learn's perception, we didn't specify any of these initialization. Because basically the perception, this module, doesn't allow us to. It will initialize all the parameters randomly by itself. So that means we only need to give the learning rate, and then it's randomly initialize all these parameters. And starting from different initializations, the training results will be different. So the weights and the bias will be different, but they are both correct. Note that even though we learn a different perception, it's still correct because as long as all the training data can be correctly predicted, we see that, okay, it's a correct perception. It's a perception perfectly matching our training data. So any questions so far regarding this implementation using scikit-learn? Yes, please.
So can you still manually input the initial weight or bias if you want to have a desired initial parameter for it?
If you use scikit-learn, you can't do that. Scikit-learn doesn't allow for this. Scikit-learn doesn't accept the argument for the initialization. For this perception module doesn't accept this initialization. So basically, if you want to use scikit-learn's perception, you have to accept that the module will randomly initialize all the parameters for you. You can only decide the learning rate.
Will the final weight and bias be the optimized bias and weight, or you have to find another way to optimize it?
This is already optimized. So there is not unique optimized. So as long as it can correctly predict all the training data, we see that it's already some converge to the optimum. Yes. Actually, that's why this module doesn't care about the initialization, because it only cares about whether at the last it can correctly predict for all the training data. The weights and the bias, they are not unique. Very good. Any other questions for this implementation?
Does that mean there's a range for the weight to use?
Yes.
Within the range you're licensed, the
Yeah, actually there are infinite number of perceptions can correctly predict for this training data.
So like a continuous range or a discrete
Continuous range.
of like that's like they continue like with lower bound and then upper bound and within that region.
It's not exactly like this. Actually, this is a very good question. Actually, we can first see, sorry, not here. Yeah, very good question. Maybe we can try to see in the visualization of these 4 data points. Let me find a good pen for this. Okay, let's see what are our 4 data points. 0, 0 here. 1, 0 here. 0, 1 here. All of these 3 points correspond to one class, right? The class 0. Another data point 1, 1 is here. We use different color, the red color, to indicate that now it's a different class with the class label 1. If we want to learn this perception to try to correctly separate the 4 data points, correctly classify the 4 data points, basically that means we want to draw a straight line. Note that it must be a straight line, because everything here is linear. It's a linear weighted sum. We want to draw a straight line to correctly separate these 2 classes. We have many ways to do that. This is one way, right? If we draw a straight line here, correctly separate the 2 classes, because we won't only care about these 4 data points. And note that we have infinite lines to separate them. Like if we just try to modify it a little bit, like here, it's another correct straight line to separate the 2 classes. So as long as W1, W2, and theta, they can define a correct straight line for these 2 classes, we call it a correct perception. And actually for this straight line, we have a terminology for this. Later on we will mention that. This straight line we call a decision boundary. In 2D space, decision boundary is just a straight line. So, and since it's a perception, the decision boundary must be linear. And we have infinite decision boundary lines to try to separate them. Actually, that's why starting from different initializations, you will end up with different weights and bias, but all of them are correct because all of them can correctly match with our training data. Our training data only have these 4 data points. Very good question. Yes, thank you. Any other questions regarding this implementation? Yes, please.
What's the physical meaning of the learning rate?
Learning rate, yes, very good. Learning rate here is used to adjust, like each time, how many value or how many lengths you would like to update your parameters. Yes, so basically that's if we get the updating rules here. Here. So it controls the number of values that you change it. So if it's very small, then that means you want to change all of your parameters slowly, very, very slow. If the eta is very large, then that means you want to change your parameters very quickly so that each time, each step, if there is a mistake, you will just modify it a lot so that it can just try to be closer to your target. But this eta, if it's too large, it's not a good thing because it's too large. It may be just jump over the optimal value. So, but if it's too small, then it will be very, very slow to get the correct value. Yes, so it used to adjust the value and also adjust the speed of the learning. So here, in this example, we use eta is 0.2, right? And we finish it with 3 rounds. So after 3 rounds, we get convergence. If we change the value of eta, then the number of rounds may get also changed. Like if we let eta be very small, like for example, if now we let eta be 0.001, then possibly we will need many rounds to finish the training so that it can get adjusted to the correct one. That's a very good question.
It's usually between 0 and 1.
Yeah, usually it's just between 0 and 1. Yes, very good. Thank you.
What is the gradient? What's the gradient of the graph, and like how does W1 and how do W1 and W2 being represented?
What do you mean the?
Like, because W1 should be the gradient of something.
W1 is not the gradient of something. W1 is the number associated to the input, the x1. If we want to update W1, we need to get a gradient to update that.
Like, is it some kind of gradient that could be?
Yes, actually, yes. Actually, the gradient is this one. The arrow times x1 is the gradient for W1. That's why we update it using this one. Yes. Yeah. Very good question. Yeah. Any other question? Yes, please.
If we use the same data to run the scikit learn model twice, so will be the parameters be?
Yes, possibly will be different because each time it uses different random initializations. So you run it twice, then yeah, possibly you get 2 different. Yeah. Thank you. Yeah, thank you for your questions. Your questions are really good. Very insightful, actually. Great. Any other ones? All right. If no questions, then let's take a 5 minutes break. After that, we will continue. To explain about the decision boundary, so that we will have like a formulated decision boundary concept.
like for n, you have to like stretch it into a factor. Like when it is a 3D array, can it still stretch it into a factor? Because I've
Yes, it's one way that you can do that, but usually if it's RGB, we directly CNN. But CNN is separate. CNN is different. CNN can accept some string.
so you can keep the spatial of the
75分写的25分判断题，特别难想不出来，不是就特别多，就是特别多。就是2012那个，不是他那个 Spring， 你们去年那个 Spring 和之前那个 Spring 风格差别太大了。不是你们75分写代码，不是你们命多少？你们去年命多少？60多。他要那么考，真的不是特别难，对啊，写代码就写211，对啊，这个。但是他就是没有写不出来的，但就是特别多，基本上写完差不多就可以收卷。
Alright, let's come back to our perception learning. So now you already know the steps of like how to update the parameters for perception, right? Given a training data, just follow the updating rules, iterations by iterations, until you get convergence, until you like reach some termination condition. So here is the stopping rules. Like when should we stop this iteration, stop to learn that? Usually we have like these 3 ones. First, we can try to use some maximum training time. Actually, it's also it's a little bit like the second one. The second one is like the maximum number of training cycles allowed. That's the max iteration. Like in our manual iteration, our manual implementation, we just use this 100 as our maximum iteration. So if the maximum number of cycles exceeded, then we just stop it. Here, use the maximum training time is a little bit similar, but now you set a time. For example, you said, okay, I just want to train this perception for 10 minutes. Then after 10 minutes, it should stop. I know that the training may go a bit beyond the specific time limit. Like if you set it to be 10 minutes, possibly it will spend 11 minutes, something like this, just a little bit beyond in order to complete the current cycle. So still it needs to complete a whole cycle. A whole cycle, that means a whole cycle of all the training data. The first two, like they focus more on like try to restrict the running time of the whole process. The third one use some minimum, it's not minimum accuracy, it's like minimum change of accuracy. Sorry. So the training will continue until some specified accuracy is attained. So you set an accuracy threshold or an error threshold, and in that case, so if it reaches this threshold, then the training just stop. So you have these ways for these stopping rules. And you may ask that why? Why not we always set the stopping rules as convergence? Convergence means that in a whole cycle, no mistake is made by the perception. Just like previously, in our manual calculation, we stop it because we reach convergence. Like the last cycle, the last round, no mistake is made by the perception. This is called convergence of perception. You may ask that why not always set the convergence as the stopping criteria? Because it's not always converge. Perception is not guaranteed to converge. Perception converge only if the training data is linearly separable. Perception, after all, is a linear model. It can only try to separate the linearly separable data. If the data itself is not linearly separable, then the perception will never converge. So that means in all the iterations, no matter how many iterations you run, there will always be some mistakes. You cannot reach some cycle that's no mistake at all. Basically, that is the data cannot be learned by a perception. Then the perception cannot get converged. So that's why usually when setting the stopping rules of perception here, we don't always require the convergence because convergence is not guaranteed for perception. And let's see more. So later on we will talk about sometimes why it cannot converge. So first let's see some terminologies about learning and epoch. Previously we just roughly used some terms. Now let's formally define this terminology so that later on we can all in the same context. Learning, we already know in AI, in machine learning, learning is basically training, right? Learning is the process of updating weights and actually also biases. So learning is the process of updating the parameters in the perception. Like for example, previously we set weights W1, W2 initially, but of course it causes some errors because we randomly choose the values. Then we update the weight value to 0.5 and predict all instances correctly. And the whole process takes 4 runs, or here in terminology we say it epochs. Epoch refers to one cycle through the full training data set. Previously, we roughly used some terms like runs, like iterations, but in artificial neural network, actually we have the terminology to call it. It's just called epoch. Like previously, when we do manual iteration, the manual calculations, we have 3 epochs. So we can just use this epoch to refer to one cycle. Then we can further make some observations. According to the results of the perception learning procedure, finally we get the parameters like this. And the relationship between the inputs x1, x2, and the output y actually is like this, right? So y will be 0 if the binary step activation function is smaller than 0. So that is if 0.3x1 plus 0.5x2 minus 0.8 smaller than 0, then the output should be 0 and it's 1. Otherwise, we can try to rewrite it into this way. So if 3x1 plus 5x2 smaller than 8, then y is 0. Otherwise, it's 1. This is a straight line to separate the output to 0 and 1. And this is what we call decision boundary. So the straight line defined by this is called decision boundary of the perception. By definition, in a binary classification problem, a decision boundary or sometimes decision surface is a hypersurface that partitions the underlying vector space into 2 sets, one for each class. Like here, the 2 straight lines, they are decision boundaries. They just try to separate all the vector space into 2 classes. And the classifier will classify all the points on the one side of the decision boundary as belonging to one class, and all those on the other side as belong to the other class. So that is, using the perception and the training data, you will learn a decision boundary. What is this decision boundary used for? Later on, when you do testing for some new data, you just do the prediction according to decision boundary. So let's say this one, suppose we just keep 1 is okay. Suppose we learn the decision boundary like this. So after training, we get a decision boundary like this. And that means later on, if you get some testing data, if you get a testing data here, so this is some testing. Then according to the decision boundary you have learned, you should classify this testing data into class label 0, right? It belongs to this class which share the same class label with these 3 points. And if you have a new testing data lies here, suppose this is another testing, then you should predict it to have the class label 1. So the decision boundary is used to do the prediction later on. And when we say that we learn a perception for training data is equivalent to we learn the decision boundary for the training data. That's why there is not unique perceptions for a training data, because there is not unique decision boundaries for a training data set. So this is the concept of the decision boundary. And let's say a problem about sometimes the perception cannot converge. So can we apply the same perception learning procedure for the XOR gate, the exclusive OR logic relation, which has a choose table like this. So when x1, x2 is 0, 0, the output is 0. When x1, x2, like they are different, like 1 is 0, 1 is 1, then the output should be 1. If both x1 and x2 is 1, then the output is 0. So the truth table is like this. Can we learn a perception for this one? Actually, no. A perception cannot implement this logic relationship. No matter how many epochs you tried, your perception never get convergent. No matter which initialization you tried, your perception never get convergent for this data set. The reason is that the data itself is not linearly separable. If we try to visualize these 4 data points like this, you'll find that these 2 data points belong to one class. These 2 data points belong to another class. In this 2D space, you can never draw a straight line to separate the 2 classes correctly, right? No matter which line you draw, actually there must be some mistakes. So you can never draw a straight line. Straight line, what is straight line? Straight line is the decision boundary of a perception. That means you can never get a perception who has a correct decision boundary for the data set. So this perception simply failed for the data sets. So that's why we see that perception is not always convergent. Like for such data sets, the perception never converge. If you try to use perception, then you must make some mistakes in any of the epoch, and then you will just have some infinite loops if you want to get convergence. Then how to solve this problem? If we really want to learn a model so that we can correctly classify these 4 data points, how should we do? Then we need to refer to our next lecture's topic, that's multi-layer perception. Because multi-layer perception will add the non-linearity to some single perception, to some single neurons, and the non-linearity will be used to deal with the non-linearity lies in the data set. So until now, any question? Any questions so far? Yes, please.
For the slide, like 37, like you mentioned about the accuracy will not like always be 100% because of you not like always converge, right?
Right.
But will the final bias and weight set overfitting on the testing data set? Because like for the previous model, the KNN model, like we will use default method to try to make it not overfitting on one data set, but in this terminology, it's always just use the same data set to test it.
Yeah, theoretically speaking, the overfitting may happen, but practically, usually for the perceptual model or for the neural model, the overfitting doesn't happen so much because they are too simple. If the model is too simple, then usually the overfitting problem is not so severe. It's not happen so frequently. But if the model is very complicated, like later on when we learn MLP, when we learn CNN, you will find MLP and CNN will overfit a lot. That's overfitting only like in practical only happens for some complicated models. Very good question. Thank you. Any other questions? Great. If no question, again, we have some practice problem for you so that you can try whether you already fully understand the process of perception learning. Try to learn a perception for this data set. It's the logic OR. And after that, you can try to compare your answers with this. If you want to finish the whole training, basically you need so many epochs, so many steps for that. All right? Then the last a few minutes, again, we can leave some time for a quiz. Quick response to see whether you already have the basic understanding of the artificial neurons. So let's scan this QR code to join this Mentimeter quiz. All right, so has anybody joined yet? Great, then let's start. Let's start the question 1. Okay, supervised learning. When we learn the artificial neuron, we use classification as an example, right? Classification, of course, it belongs to supervised learning. And actually, the artificial neuron can also use to do regression. But anyway, they all belong to supervised learning. We must have the labels to guide the perception to update all the parameters. If you don't have the labels, basically that's the target big T, right? If you don't have the big T, you don't know what is the error, and then you don't know how to update your parameters so that it can get closer to the target. So artificial neuron is used for supervised learning. So let's check the leaderboard. Okay, number 1 is Elsa, and question 2. Okay, this is true. Yeah, I think the majority can get that. The ultimate aim, like the final result, what we want from the perception is just a decision boundary that can separate the training data set into the different classes. So this is the ultimate aim of a perception. Basically, that's the results of the perception learning. Okay, Elsa is still our number one. Right, then the next question. Should be the bias is independent of the input. Weights are dependent on the inputs, right? Basically, the weight is some value associated with each input, and if you refer to how we update the parameters, how you update a weight absolutely depends on the inputs. But how you update a bias term does not depend on the input at all. It only depends on the learning rate and the error. So actually the bias term, which is associated with the neuron itself, tries to make the adjustment independent of the input and improve its flexibility in learning, right? The weights already associated with the inputs. So this correct one is bias term. Oh, that's very close. Yeah. Now our number one is this Chuyi. Yeah. All right. Then the next question. Okay, this is false. Actually, when we introduced the binary step activation function, we mentioned that binary step activation function can only output 0 and 1, two possible values. So if we want to use the perception must use binary step activation function. Then that means we can only have two possible outputs, can only use to do the binary classification, cannot do multi-class, right? Two possible outputs cannot correspond to this multi-class. So that's false. Okay, number one is still true. Last question. Okay, this is true. Activation function, yes, it can be used to add nonlinearity to neurons, right? So previously, the binary step activation function cannot, but other activation function, actually, yes. Like the sigmoid activation function we have learned, it's a nonlinear function. If you still remember, it had this S shape. Like if we have some nonlinear activation function, actually it can be used to add the nonlinearity to neurons. And this is the motivation for why we should add activation function in multi-layer perception to deal with some non-linearly separable data. So this statement is true. And finally, let's check our final leaderboard. Wow, congratulations to Zhu Ying. By the way, who is Zhu Ying here? Oh, congratulations. Yeah. All right, so yeah, that's all for today's class. Thank you for participating and see you in next week. Please remember to attend Lab 5. Attend Lab 5 on next Monday or next Tuesday. Okay.